喂，能听到吗？好像有事。是，哎，等碰到哪里了？可能走路会发出额外的声音，不过应该还好。Okay. Shall we start? Okay. All right. Thank you everyone for coming today. This is the fourth lecture in the series about Entanglement Bootstrap. In the weekend, we'll get a brief overlook of the gapless version of Entanglement Bootstrap. Now we come back to the gapped version. By the gapped version, let me briefly review. The idea was that you have a many-body system made of many qubits. So they have some qubits spread on some integer dimensional space. We consider 2 plus 1D, for instance. That's the context that we have anions. We have, suppose we pick a piece of the wave function from the many-body system, like this, on a topological ball with no interesting topology to start with. Um, we want to understand the the phase of matter and the emergent properties, like whether there are anions in the system, how many anions there are, or why anion is a reasonable description of the system. And we count the number of anions and ask how many anions are there, how they fuse with each other. Are they all abelian anions or some maybe non-abelian ones, and can we justify the breeding properties? Whether they breed non-trivially and what the self-statistic and mutual breeding statistic. Only with this piece of wave function. Of course, we need to make some assumptions. So the starting point was, okay, this reference state given to you satisfy two axioms, A0 and A1 on those local balls. With that information, okay, I'll review the fusion property, what we learned from here. Fusion and so on. But today the main topic would be how to understand breeding statistics. There are two different point of view of the breeding properties. One is that you have a multiple state closed manifold, and then you do modular transformation, for example SNT and so on. And then you can see from those matrices that the breeding property of anion should be like what? Like you have some representation of the on the torus you have the modular S and T matrices, so you can play the same game on like higher linear surfaces and so on. That's one viewpoint. Another viewpoint is that you have string operators. The breeding would be correspond to, like, you have anions create anion pairs. Yeah, let me draw a figure. It's like if you have a space time, time and space, actually two-dimensional space X and Y. What you do in field theory is that you create a kind of a Wilson loop with A and B, then you get matrix SAB, which is related to the mapping class, the S transformation. And yeah, so you have a different way to describe the S matrix. Both viewpoints are can be reproduced to in the entanglement bootstrap formulation. I'll comment on how to understand the string operators as well. Um, But if I take a focus, I would say the main story I want to tell is that if we look at the density matrix and the set of states that locally look like the vacuum and try to play some topological tricks on them, we can learn a lot and hopefully everything about breathing. Okay, so let me give a brief review on what we learned. So the an animal species. So what we learned is that once we have axiom A0, well, the reference state, some reference state, any reference state with axiom A0 and A1, we can define the concept of a information convex set. So that's a set of density matrix on some region omega satisfies some condition. First, it's reduced from another density matrix on a thickened region. So omega plus is a thickening of omega. And if you reduce this, you get your omega, and with some requirement on omega delta on a larger region. So for any ball contain in omega plus, this thing will be the reference state on a ball. For any ball contained in omega plus. So if I draw a figure, that would be, so you have your omega with some interesting topology, let's say. And we thicken it, so within the dashed line, that's omega plus. And then we find some local ball B like this. Either this one, this is the one choice of B, this is another. Yeah, so the intuition that we have a set of locally indistinguishable states. So intuition locally set of states. Okay. So they are locally vacuum in some sense. So if we think of the reference state on the large ball as the vacuum, then this is a set of locally vacuum-like state. So they're kind of trivial. You don't see excitation anywhere on omega. Anywhere on omega is looks like the vacuum. But nonetheless, the set is non-trivial, and there are facts we should review. So first of all, on a topological disk, yeah, so you call that here omega, we assume that it's embedded in the background. I'll comment on the generalization, but that's what I told you about. Yeah. So one simplest embedded region would be the disk. It turns out this one is trivial. Trivial in the sense that you have a unique element. The element is nothing but the reference state reduced to the disk. I think it's intuitive. But then the next one is more interesting. The information convex set of disk. Yeah, I draw the irregular shape intentionally to just remind ourselves that it is logical. Doesn't matter what the shape and the size of the annulus is, as long as it's larger than the length scale that we impose the axiom. We impose the axiom on those smaller length scale and then what I said will be true on the larger length scale. It's a set of PA A with a set of 16 points. A extreme point. And that's a finite set. And so pictorially, I could draw a simplex, or a triangle is a simplex. A tetrahedron is one as well. And in particular, if we have a Curry code, the Curry code. Pick the Curry code with function that's a valid choice of the reference state. Indeed, you get a simplex and with 4 extreme points, so rho 1, rho E, rho N, and rho F correspond to the 4 different types of anions. So in fact, in entanglement bootstrap, the way we define anions the set of anions will be defined as a set of extreme points that are labels of the extreme point, or of the information convex set of the annulus.
So which condition implies the finiteness?
Good. So the finiteness follow from the assumption of a finite dimensional Hilbert space. On each local patch you have finite dimensional Hilbert space, and I assume that the annulus is a finite collection of local sets.
Thank you.
You can replace this by other assumptions as well. Like suppose the subleading term doesn't blow up, then you also can say the same thing.
Is it that if this is some flat but describing some irrational things, then maybe the correlation length is still very far from 0 at this intermediate scale.
Right.
And then that's how we distinguish it from finite.
I believe so. I more generally, I believe the following is true without proving. So if we have some mild intermediate length scale, and suppose the axioms are already very good, like the array is tiny and its decay is fast, then probably we can also show it finally. And the vacuum sector among the anions, among the anion sector, there should be one special label called the vacuum. The vacuum sector, I call it 1, it defines such that U of 1, the vacuum state on the annulus, is nothing but the reference state reduced to the disk. Right. I hope this is clear. And now let me make some comment on the string operators. So it's like traditionally, if you have a solvable model to play with, you have Curry code, you have your string net. So people say, oh, anions are excitations of the model. So you have some anion appear in some places. So comment on solvable models. Solvable. For solvable models, you have local Hamiltonians usually. And exactly solvable models would be particularly nice if you want to learn anion. And there are such models. And if you play with such models, you will find you can create excitation, the anion A somewhere, and you have a string operator. String operators, if you have an infinite plane, you can push the anion to infinity, but on a finite lattice, you need to have an antiparticle somewhere. Yeah, if you have a finite disk. But then the viewpoint is, oh, we should look at the excitation. That's one intuition we had. Excitation. And we can move them around, right? So like we have A and B, we create anion pairs, and we can place them around, fuse them, and so on. And yeah, but now it looks like we are not if we look at information convex set, we were trying to look at the excitation, not by looking at it, but rather looking at detecting annulus around here, right? And this is a very general idea. To make it more precise, I can say that when we look at the anions, or if we think about the state on a sphere, if we look at the state on a sphere, suppose on a sphere you have a nice state. Well, let's say it's entanglement bootstrap state. In the sense that all the axioms A0 and A1 put everywhere on the sphere. Then we if we have anions that's A and A bar, you must have the anti-anion somewhere. And the annulus, what's the annulus? We choose the annulus would be the complement, the complement of the excitation. So this is a large annulus. So in other words, the idea can be summarized as we are looking at the complement of the excitations. The complement. And we can try the same thing for the configuration with 3 anions. Okay, A, B, and I think very good to have, let's see, bar, B and A and B. Okay, so still on a sphere, we look at the complement. The complement will be a two-hole disk. And indeed, in the previous lecture, I think lecture 2, that we defined a fusion space. We find that in the information convex set of this two-hole disk, with some restrictions on the label, we have a subset with label A, B, and C on it. It's isomorphic to a state space of finite dimensional Hilbert space, and the dimension of V, the vector space, are some integers we call the fusion multiplicities. So in other words, the set of labels of anions and the set of fusion multiplicities, it can be figured out by looking at the complement of the excitation. So that's a valuable idea. It's like if you know something about the quantum memory aspect of logical order, maybe this will be more obvious. It's like you have a state on torus. You can have multiple locally indistinguishable states to allow you to store the quantum information. You don't see the excitations anywhere, but you get different states. The idea here is the same. You have different density matrices on the complement of the excitation. They knows about the fusion space. They knows about the anion species. In other words, the property of having a non-trivial anionic excitation or in the topological order Actually, this is true in any dimension. That yeah, those excitations are the property of the vacuum. So you can detect that fusion space and anions from looking at the vacuum rather than the excitation. And the spirit of this talk will be try to develop as much as possible from the viewpoint of playing with the vacuum. Yeah, also what can we learn by the state of the on the vacuum rather than relying on string operators and excitation. But let me do comment on the fact that the string operator exists. So the other viewpoint is consistent with the entanglement bootstrap. So once we have the simplex theorem, we're not very far away from showing that a string point can only be created by string operators a and a bar existence. Or string operators. That's a theorem, and not only that, you have a string operator connecting a and a bar. You can have a string operator with a 3 or more endpoints with a multiple anions, and in this way we recover the traditional intuition you had if you played with the double lattice model. But more about this will be in the next lecture. I won't talk too much about it in this lecture. But let me comment that if the anions are abelian, the string operator is a depth 2 circuit. It's a finite depth circuit, a constant depth circuit. Some people call it shallow depth circuit. But if anions are non-abelian, you need linear depth circuit. If you push anions further apart from each other, you need to increase the number of layers of gates you apply to the system. Okay. Exactly. Right. Now let me. I'm going to start to be very fancy in the next, because I'm going to say that the previous time this thing I told you was not the most general one. So if you look at the definition of the information content set, what the key thing is? The key thing is, of course, you need a reference state, and yeah. So alternatively, we can write this thing as given some region omega and your reference state, right? Because you need to put the system this region on the background that you have a physical qubits. You have qubits, then you have a region subset. And then you define a density matrix on this subsystem by requiring some consistency. So first we want to be able to thicken the state a little bit, but then well, there's some replacement of this one. If you don't want to thicken it, you can impose some additional condition, Markov state condition near the boundary. Yeah, this one can be replaced. But the second one, so if we try to think about the second one, it says that we only need some local consistency. And in fact, to have this one, we don't need the region to be embedded into the system. So let me give you some example and try to motivate this. Um, right. So okay. So let's try to construct a density matrix on a region that's not embedded on. Okay, so let me start with yeah, let me do a disk actually. It is a randomly chosen or something. So this arrow says it's a standard notion of immersed region. Immersed and local embedding. So one instance is the trivial embedding. So like embed the region in it is certainly also a local embedding. But you can do more interesting things. You can like this. This is an immersed disk. I know it should be confusing, but the idea is that you have a map from this topological space to the physical background of your lattice system. You have many qubits. You assign this qubit to somewhere. The first qubit is here. Let's see. This part is the neighborhood of this side. You map it to a disk, so it's locally embedding. But the other half of the disk, you map it to the background. You also get a disk is this part, the blue part. Yeah, both are locally the disk, but they map to be on a qubits with overlap, so that some qubits are used twice. It's okay because it is still a local embedding. So given such a region and the structure of a matching from here to there, you can pull back the Hilbert space from here to the topological manifold. So the Hilbert space there is larger than the image. So the image covers some qubits, but it needs a few more qubits to define this quantum system. And you can think about the state on such a larger Hilbert space, the Hilbert space over here, and with some consistency rules define analogous to those ones. So you can convince yourself that for any immersed region, any omega immersed in the background, you can still define the information content that we have sigma omega defined. Okay, but is this empty? Like if I take the immersed disk, this one. Yeah, the first question we can ask is that whether it's empty. Any finite time is okay. Yeah.
Bowen entropy with this disk that where a qubit is used multiple times, and do you mean if I when I take eigenvalues, so compute entanglement entropy is to look for eigenvalues. I have this number of qubits, but then this qubit is used twice. Then what do I actually do when I compute these eigenvalues? So do I do replica trick, and then when I glue, I carefully use it twice? How do I actually compute entanglement?
That's an excellent question, and replica trick maybe, but for this one we have some other tools. The way I compute this is that, well, suppose you have some state, then we chop this into pieces like A, B, and C. The ABC is inverse, right? It's non-trivial.
Right.
Yeah. But if we look at AB, the AB is actually embedded.
Yes, it's normal.
Yeah, it is normal, right? So suppose we somehow know the state is a Markov quantum Markov state. Then for quantum Markov state, SABC will be SAB plus SBC minus SB. Yeah, then we find some way to reduce this to simpler problem.
I see.
Yeah.
But then it's the fact that this is a Markov. If we consider so it must imply some rules in computing as ABC in this case. But I see what
Yeah. Yeah, great. And right. So the first question we need to ask is whether this is empty or not. If it's not empty, we can ask a Janet question with the entropy and so on. Yeah, good. So right. Now it's good time that I review two most very fundamental idea in Entanglement Bootstrap. That's to use to merge quantum state to to get fancier regions from simpler regions by merging the states on such regions, and to deform and as a special case you can deform the region topologically. Right. So I'll spend the two blackboards around here to develop that idea and give you some simple intuition about immersed region. After that, I will be somewhat even fancier to draw some not even more non-trivial immersed region and tell you why they are valuable in terms of understanding the region statistics. Right. Merging quantum state. The case statement is the following. So and then be abstract proposition theorem and so ABC. Yeah, given to state your ABC then BCD defined and the merge state ABCD defined as the merging. If rho and lambda satisfy some rules, the I HCD of rho is 0. And how satisfy how is the state on ABCD? Now we reduce this to ABC, it will be identical to rho. How reduced to BCD would be lambda BCD and it's Markov. Well, you may wonder how about I A B condition on BC? It turns out it's also zero. It's just some corollary of the previous line by strong subactivity. It follows for free. So intuitive picture is you have some state on ABC, another state on BCD, and somehow you can merge them. Have um ABCD, Q and lambda. Well, this is for general quantum state, but a non-trivial statement is that it works for information convex set, which is important. If you lambda from information convex set about B, C, and D, then tau. Yeah. Oh, good. So the existence is very important. Yeah, we don't need to know there is a state beforehand. We just need to know the pieces and property of the pieces, then we can construct such a state. It is important. The second important thing would be the local indistinguishability. So it is identical to rho and lambda, and that is Markov. It is a Markov in some sense. It's saying that it's the maximal entropy state among all the ones that consistent with the physics. Right. So this is because the entropy, yeah, as tau is yeah, it's equal to as UABC. Yeah, I'm applying this one. Lambda BCD minus S UBC. But for any other state you will have less or equal to. So the Markov state, the maximum entropy state among all the ones consistent with the pieces, or in some literature it's called consistent with the marginal. If you, I don't know how many you heard about the so-called quantum marginal problem. Is the problem of finding some state that's consistent with the local pieces. We call it consistent with the marginal. In general, it's a hard problem, but if you some Markov state, you can prove there exists such a state. It's some solution of quantum marginal problem. And right, so this big theorem I sketched here, this part is known in quantum information literature without talking about information convex set. But borrowing such tools to entanglement bootstrap will be somewhat give some fancy conclusion based on the fact that you can play with a state in the information convex set and the end state with the result in another information convex set, and such state can. Oh, I guess that's what I'm going to recall next. That the information convex set is topological. You can topologically deform the state, which is actually a corollary of this. So let me recall the important theorem of isomorphism theorem. It says if we can deform omega to if omega can be deformed to omega prime, let's see on the background. So the background we will see, oh, it's a disk. So if it's a disk, I'll make the drawing. So I will say this one filter, the other one is saying omega can be smoothly deformed to omega prime, then the two information convex sets are isomorphic. The proof sketch is the following. The proof sketch is to use merging. So you have your omega is BC. Let omega be ABC. Now omega prime is ABCD. Sorry. Okay, ABCD. So ABC, let me draw it this way. So A is here. So let me draw it bigger. So A, B, C, and D. So from ABC to ABCD, you actually deform the boundary. Yeah, so deform the boundary from here to this one by adding a bump locally on the entanglement boundary. Yeah. So this is your previous region, original region, and then you deform this by any finite sequence of the elementary step of extension or the inverse, partial trace to get rid of some regions to remove the bump. It's okay. So yeah, those are give you a sense of deformation. Once you have this, you have state on ABC. So ABC from information convex set on ABC. But from the axiom, we know that ACB of rho is 0 by axiom A1. And furthermore, the state rho BCD, well, actually BCD is a disk. BCD is a disk. Therefore, the state lambda BCD, we choose this from the information convex set. Therefore, it's just the reference state. Reference state on BC and D, and both rho and lambda reduced to BC are the same as the reference state. Therefore, they converge. Right. Yeah. So this is the most important step in showing the isomorphism theorem. But this is not all. The actual proof is longer because we need to check whether such state is unique, whether the existence is important. But once we know there exists such state, it is the unique extension of some state ABC from ABC to ABCD. It turns out it's unique. So you have existence and unique. You first extend, and then you do partial trace. It turns out to be identity operator on the convex set. So you have a map and another map. You fit the identity. It's invertible, right? Yeah. Okay. That's the proof sketch.
Sorry. I thought the uniqueness was given by the previous statement that any other state would have less entropy than the right-hand side of that formula there.
Right. So first of all, if you take any other state, the entropy can only be smaller or equal to this one.
Right.
The second, it's also true that the Markov state is uniquely determined by the marginal. So if the entropy give you equality, that give you a unique state.
Okay.
Yeah. Right. So that's an application of the idea of merging. But there are fancier versions. So let me you read the proof and draw some figures just to illustrate some non-trivial applications. So first, the idea is that you can, so this is your background, and suppose I have an annulus that my omega, and here is another annulus that omega prime. So yeah, I hope you can see that we can apply a finite number of elementary rules to add a bump and partial trace and move this annulus from the left upper corner to the lower right corner. So there's some automorphism you have. So for instance, this implies that if we know the information convex set of this one is some simplex, suppose the simplex has 1, 2, 3, 4 extreme points. And with the isomorphism, which require you to require the fact that on the path of deformation, all the axioms, the axiom A1 especially, need to hold everywhere. So you don't have a domain wall. So you have a smoothness, then you can put it in from there to here. Then this by the isomorphism theorem, it follows for free that you also have a convex set with the same number of extreme points. Yeah, which is not trivial. Given that I can immediately show you a counter example within the Torah code. But in the counter example is the following. I'm trying to say that if somewhere the axiom is broken, axiom A1 is broken, then we no longer have the isomorphism. So with defect. Well, suppose this is the Torah code. For the Torah code, on the annulus surrounding no defect, we know there are exactly 4 extreme points labeled by the 4 annual species. But suppose there is a defect here. E and M exchange defect. So the defect has a property that if you surround move a particle, E particle around it, it becomes M. If that's the case, then it turns out we know two things about the defect. So first, on the defect, the axiom A1 is violated. So if we draw this strips the B and D, the configuration where we compute axiom A1 check the axiom, check the entropy combination SBC. Yeah. So let me write here. So what we find is that the configuration looks like the following. So the first two terms are computed on disks containing the defect. And the last two configurations, they are disks and they are away from the defect. But the defect has some non-abelian nature actually. And we can compute and find if we do this, we get log 2. In other words, delta BC and D equal to log 2. So A1 is broken. So By this I mean the entropy for this configuration plus the entropy for the second configuration as well. Minus yeah, and we can check the information convex set. So it turns out indeed the information convex set are different. So this one has 4 extreme points. So if you let's call it omega, this is omega theta. So for omega theta, it turns out it has only 2 extreme points, which correspond to the two topological defects. Yeah, so it makes physical sense, and it's a non-trivial check that we shouldn't have a stronger version of the isomorphism theorem. This is as strong as we can get.
It does not cross the defect line, then
It cross the defect line. Which defect line you talk about? Defect line could be deformed. It could be this one or could be that one.
right. But if the endpoint of the defect is not inside omega,
Yeah, it's not inside omega. Right.
tilde,
Oh, okay.
then the isomorphism still exists even in the presence of.
Right. So if there were no defects, then you can deform this mostly to that one.
We
We
just
don't.
need to avoid those regions.
Yeah. We need to avoid any region that break the axioms.
Oh, put it differently. If there exist regions where I can go through to move omega to omega prime, then that isomorphism is preserved.
That's
Even though
right.
some paths would be problematic.
Yeah, that's right. Yeah, as long as you can find the path, then
If there exists a path that I can avoid this defect, then
yeah,
that isomorphism is good.
that's exactly true. Right. And this deformation of an annulus, it's kind of philosophically interesting because annulus can detect topological charge. So it's some kind of charge, but it's not symmetry charge. And we didn't assume translation symmetry. We didn't assume any global symmetry, other symmetries. But somehow we established a sense of transportation of charges. It's not not the theorem, not the most not the theorem was a really deep and important theorem in the past century when we play with symmetries, right? That's the theme of the previous centuries theoretical physics, and the theorem was a big deal. But this one was something different. But we still established some transportation of topological charges.
In omega tilde.
Okay.
Then what's the information convex set? It's still 2 extreme point.
Good. Anion. Okay, let's put some anions here.
Yeah.
Well, in Turing code you only have 1 billion anions, but I guess your question is more general. You're asking, let's put some 1 billion anions or not 1 billion anions. It turns out it doesn't affect the information convex set. It's simple. It's because we define the anions to be the extreme point of the information convex set. So there is a vacuum state.
I see, but when you like deforming omega to omega prime,
right.
It seems it has to cross the region with ania.
Yeah, but our definition of anions are objects that can be created on top of the vacuum. We know that there is a good state as well.
I see.
Right. So isomorphism theorem. Okay, this is about transportation of topological charges, but there's a lot of more things we can play with, which is beyond the intuition of pure charges. So yeah, charge is something we can fuse, and it's related to the simplex, and the simplex is tells you a piece of classical information. But actually, the idea of isomorphism, the deformation, is a very fancy in the sense that it can give you some non-trivial operation on Hilbert space as well. So let's take a look at another non-trivial example. Let's consider an immersed region. Immersed punctured torus. So it's a torus. If you wish, you can have a square with edge identified in some way and make a puncture and remove a ball. And what's left is your punctured torus. So this topological space cannot be embedded. So first, it cannot be embedded. Can't embed in a disk. But nonetheless, you can immerse it. The immersion would be, so one way to do that is to have the I'm not sure whether people can immediately notice this is a immersed punctured torus. So first of all, is it obvious this is a punctured torus? Let's check this really quick. It's like let's count the number of boundaries this thing has. But it has a lot of boundaries, so that the line, right? It's a very long, but it is connected. It turns out it's connected to have only a single end of the system, which is consistent with this one. So this one only has one boundary. But usually it takes some practice to understand the topology. But let me draw some alternative figures. Another way to look at this is you have this so-called zero handle, and then you glue one handle on it. So this is a one handle, and then this is another. Yeah. Yeah. Okay. That's another way to draw the same region. And I would like to invite people thinking about the following. Can you imagine any ways to deform the punctured torus to itself? Question. Let's call it W. So W. Yeah. Okay. Let's call it W. Logically non-trivial way. Yeah. How can we do that? Yeah. Let's keep that question, and then I'll draw some. And I'll try to start. Yeah, we will try to answer this question. This is a very important question, and will be related to bridging statistics and the topological S matrix, the S transformation on the torus. But because this is not so simple, I'll try to answer similar questions for easier case first on this platform. Or maybe let's see, or maybe on this platform. find a path. Yeah, to make it easy to describe those examples, let me first make a definition. So the definition of a path of deformation is like from omega to omega theta. A path from omega to omega theta will be a sequence of configuration of I, where I from 0 to n, such that omega I and I plus 1 are related by an elementary move. And let's try to do this on a sphere. So omega theta on a sphere. So the background will be a sphere. So here is the first problem for exercise. Let me do it as an exercise. So annulus let me first do the embed in a sphere. And let's try to come up with some non-trivial non-trivial automorphism. Let's see. By automorphism, we mean the following. We mean if we start from the region and do a sequence of deformation, then end up with the same region. The path from omega to omega to itself gives an automorphism of the information convex set. So yeah, let's try to come up with some non-trivial automorphism. Yeah. Yeah, this S2 on top of the tutor will be saying the regions are immersed or embedded. Yeah, most generally it's immersed on the background S2. So this is the background. Yeah, background space that we have the physical system. Yeah, should remind ourselves. In the last talk, I said very briefly that if we have a disk, we can complete this to a sphere, so that the two are equivalent. So yeah, I will implicitly start from that. Automorphism of this one, to itself. Then it turns out obviously there are trivial ones. So suppose the trivial ones can be constructed this way. So you have your sphere, and you put two markers here, and we require that when we deform our region. So this is your annulus. Suppose that we require that under the deformation of the annulus, we require it to well, actually I think one marker is enough. So require this to not touch the marker. Yeah, no matter what you do, you can do it in different ways and deform it back. It turns out this is always trivial. Trivial one is the deformation. Yeah, then what's the non-trivial one? Non-trivial would be if we flip like a rotation. 180 degrees pi rotation on the axis. And so what's the difference? The pi rotation on this axis will correspond to switching the two disks. The complement of the annulus is the two disks. Or if you wish, you can think of annuls and anti-annuls on the two holes, and you want to switch A and A bar. Then it turned out this is non-trivial. And in fact, that's one way to define antiparticles. So this non-trivial automorphism, itself, let me give it a name, phi. So phi acting on extreme, one of the extreme points will give you that correspond to the antiparticle. Right. Yeah, we can check that if we do it twice, it's identity. Yeah, so the definition of antiparticle makes sense, and it's equivalent. It's also equivalent to the definition of A bar. And this is equivalent. You can check that it's equivalent to the other possible definition of antiparticle. So that A and B. So there is a unique A bar is defined to be the unique choice of B such that information convex at A, B, one of the true hole disk is non-empty. Right. So if you have a sphere and you have an embedded region, you can already hook up with some non-trivial automorphism.
It is unique.
Okay, let me see. Okay. Yeah, maybe I could prove it. The uniqueness would follow if I deform this thing on a sphere. So A, B, and 1. Suppose you know the existence of some B, and then you deform this on a sphere. On a sphere, you deform. It turns out you can turn this entanglement side entanglement boundary to the interior and turn B to the outside. So it will be A1 and B bar. Sorry, deformed. Turn inside out, then you can fill in this puncture. Fill in this puncture by merging a vacuum state. And then it will become A and B bar. Yeah. But on the annulus, we can transpose the information from the annulus near this edge to the annulus near the other edge, so we know that it must be the same. And this delta and B and A bar. Sorry, yeah, B and A bar. All right.
When we look at the this information complex of this this a pair of pants, yes.
Okay.
is there already a constraint that the thing that can fuse with A to 1 is unique?
Fuse A to 1 is unique. Yeah. There is another way. So I just think this is a somewhat more interesting. But the other.
Sorry, what I mean is here, you use the fact that B can be moved to the outside and the identity.
Yeah. So yeah, we can do this on a disk. For that, I want to define the quantum.
Oh, as in then you are equivalently, it is equivalent to say A fusing with the vacuum state has to be unique, has to be one dimensional.
Yeah, so yeah, it turns out it's related to the fact that in a B is a delta function, delta B a bar.
Right, and you prove this from how do you prove this from what property this would follow?
Yeah, there are two proofs. First, we need to prove the existence. Second, we need to prove the uniqueness.
Right, absolutely.
And you are asking about the uniqueness proof, right?
Maybe also existence.
Yeah, existence is related to merging. Merging is related to the existence of some state. Yeah, it's a merging with a entanglement cut like this. So if you cut this way, you get an annulet, then you get another annulet. So it's like two annuli. One contains a vacuum, is a vacuum sector, another is A. Yeah, you can merge the two states by gluing on this entanglement cut. So you want to thicken this cut. So that's the region we call it BC. So remember we have state on ABC and state on BCD. So the thickening of the red part is a BC. And we can find Markov state, we can merge them. And then there must be some set that may or may not be unique, but the uniqueness follows from some other arguments, such as the one I show you. But there is another one, a different one, based on the definition of quantum dimension. Yeah, so I do need this definition of quantum dimension for some other purposes. So let me write it down. C C C C C. Yeah. So quantum dimension of extreme point. Take an extreme point from the annulus. The set of extreme point. Yeah. Yes, the set of extreme point of the information convex set of the annulus, and partition this thing as a BCD as shown in the figure. And then the quantum dimension D of A will be defined to be exponential delta BCD divided by 4. And we can check that this is the same with the other definition I showed you last time. The exponential f of a, yeah, dA is this. Where f of A is the entropy difference up to a factor. Right. Right. So this definition in terms of the entropy difference, yeah, we see this is the invariant kind of deformation, and it's require the knowledge of two states. One is rho of A, another is a vacuum state. But the advantage of the other definition I show you here, well, it requires some fancier partition, so it looks harder, but it is simpler in the sense that you only need one state. So you only need to compute this on a state U of A. U of A. Yeah. Delta is the entropy combination used in the accent, right? All right. So with that, I can continue the story of immersed region and their deformations. All right. The next thing I want to talk about before answering this question for the punctual torus will be about the next simplest inverse region in my opinion. About inverse figure 8. Anyways, suppose we want to immerse annulus into the background. There are a couple of different ways. We can first make the embedded annulus. That's an obvious choice, and you can make a figure 8. That's another choice. And you can easily convince yourself that this thing cannot be deformed into the figure 8. Why is it impossible? Is from the turning number. So they have this has a 0, turning number is 0, this is 1. But how about make a region with a it's still a different turning number, right? Yeah, turning number 0, 1, and 2. 0, 1, and 2. Sorry. I think the turning number of figure 8 is 0. 0, 1, and 2. Yeah, something like that. So they should all be different. Then by smooth deformation is impossible. By smooth deformation, remember we mean in this. Yeah. Yeah, deform on the background. Yeah. Right. And yeah, and there is a topological term for this in differential topology called regular homotopy. Yeah, it's like you need the background. Yeah. Otherwise, well, you know that they are homeomorphic. They have the same topology in that sense. But here we need another sense of a topological equivalence. So they are not the same. But this one and that one also not the same. like no, I think I made a mistake. So this one, so this had a triangle number odd. Sorry, one is an odd number, right? Is odd. This is even. Yeah, this need to be another odd number. But anyway, so they are not the same on a disk. Disk D2. If the background is a disk, you cannot turn this one into that one. But we are very lucky. We have a sphere. If we don't have a sphere, we can complete this to a sphere, and then try to deform this to that. It turns out they are the same on a sphere. Do this on a sphere, you can smoothly deform this one to that one. So they are not so different. It turns out the equivalence and their deformation on a sphere are just two classes of annuli, are exactly these embedded annulus and the figure 8 immersed annuli. Immersed. Okay. And therefore, since we already understand about this embedded annulus, this figure 8 sounds like a natural thing to consider next. And there are several things we know about figure 8. So first of all, we know that the information convex set of figure 8 is a simplex with the same number of extreme points, the same number of extreme points as the ordinary annulus. Yeah, and I would say I know one proof of this, but it's not trivial, so I won't be able to show you today. And not trivial. The second one is that you take figure 8 by 180 degree pi rotation gives generically gives a non-trivial automorphism. The intuition is that if we color the two edges of the figure 8, yeah, and like the embedded one, the edge goes in and out. So if we turn 180 degrees, the two different colors are swapped. Yeah. Okay. So those are something we know about figure 8, but there apparently is already a puzzle, and it's related to this definition. So let me try to motivate this definition and why this is crucial for understanding immersed regions. The intuition is that for immersed region, we don't have the vacuum state. So on the background, we have our reference state. That's our vacuum, a good choice of vacuum state. But then the vacuum state can be reduced to any subsystem. But for immersed regions, we don't immediately have a vacuum. Yeah, so reference state reduced to any embedded region in the vacuum, but if this is non-trivially immersed, and such as the figure 8, or also embedded disk and puncture torus, denoted like this. Yeah, then we don't know about the vacuum. That sounds like a problem. Oops. Oh, okay. Okay. Thank you. All right. Okay. Great. So for figure 8, it turns out there's already a puzzle on like what is the vacuum. Like, there. So given that, the information convection for figure 8 is some simplex, right? With the orthogonal extreme point, you gives names h1, h2, and so on. Is a set of object extreme point on the figure 8 has h1, h2, and something. And that the distant matrices are orthogonal to the other one. Well, we know that, but there's something I don't know how to answer. It's like, is there a vacuum? Do we know if there is an Abelian extreme point? Well, recall that we know how to define the quantum dimension. If we use this definition of quantum dimension, yeah, we should partition the figure 8 into this topology and then do this computation. So we do know that the quantum dimension of the extreme point is, yeah, like that. And we know it's greater or equal to 1 from strong subjectivity. So delta is non-negative. The exponential of that is greater or equal to 1. But is there an Abelian extreme point? So given any reference state, we can ask you this question: whether there is an Abelian extreme point on the figure 8. Up to now, I couldn't solve this problem in the most general case, but for Abelian model, I know the answer is yes. So partial answer. If the A is Abelian for any A, then yes. Yeah, in this case, all the dimension of HI will be 1. Yeah, so every extreme point is abelian for abelian theory. But more generally, I think it's an important puzzle, and it's related to the topological spin, the T transformation on the torus.
So wait, so I'm a bit confused when you say define ground states on this figure 8.
Figure 8. Define the ground state on figure 8.
Ground state is something like it satisfies A0 and A1. No, not really. You mean there is some notion of row 1.
Yes, that's some notion of row 1. Yeah, yeah. That's one question. Actually, that's a question not covered by this one. So this puzzle is the abelianness, whether there is a abelian extreme point. Sometimes you can have multiple abelian extreme points, but then you still want to ask which one should I call it as the vacuum? Which ones are different ones?
So whether these extreme points have a simple identification with the extreme points on an annulus, is that the question?
Yeah, I guess so.
So you get a information syntax, but then the extreme points here, what do they have to do with those on the annulus?
On the embedded annulus.
Right.
Yeah. It's like if you can find a canonical isomorphism, then you can map the vacuum to some particular state you call a vacuum. But we don't know a canonical choice at this moment. I couldn't identify the general answer. But for solvable models like string-like, like quantum double, I think there is some pretty simple way to say, oh, this one is special. This one we call it a vacuum. But for chiral state, if we don't have a solvable model, how to do it more generally, that appears to be a puzzle. Yeah.
So even if it's on a Boolean insolvable model, that would still be a natural identification of this extreme point with the extreme points on the annulus.
I believe we can identify a vacuum even for chiral state. Yeah.
That partial answer was for there exists an abelian an abelian extremal point, right?
The partial answer is based on models with all anyons are abelian.
Yeah, and then you can find the abelian extremal point. And what about the vacuum?
No, I don't know the answer to the vacuum. Yeah.
I was thinking if you could somehow consider the like the identity of fusion of the figure 8 graph. Yeah,
you can fuse. Let's recall. So by fusion, we made some progress by merging annuli, right? Yeah. Merging them, then we get fusion. We can fuse the figure 8 to the ordinary annulus as well. Okay. If they connect them, right, we get a region with 3 folds. Yeah, so there's some ability to talk about fusion, and there's a fusion space, but based on that, I'm still struggling to solve this puzzle.
I see.
Yeah.
Whether the turning number is changed when you fuse with something that is so 2 even things fused together is odd, or or even to
yeah, I think maybe +1 or -1.
right.
Yeah. Yeah, there's some conservation. It's like you cannot find a fusion figure with only one of the entanglement boundaries figure 8, but others are ordinary.
Right.
Right. Yeah, that's so.
So I wonder if the information simplex with Okay, but then after you got two turns, then the two turns at least on the sphere is equals to no turn.
Yeah, this one. Yeah, this is true.
Right. So, can you fuse two figure eight and go to that picture?
Yeah. So we do have a region with three holes. Two of the holes are figure eight. One of them is actually embedded anyway. But that didn't really help me. But I want to think more, or maybe I could ask some help to people. Yeah. But those are natural questions. So you have to face such questions. If we say, oh, we got everything, we proved the modular tensor category kind of signal charge classification without being able to answer this question, I won't be happy because why is that so? Because this is a physical question. We have a physical quantum state. We can construct such state. Every question I ask is a physical question. So if we really want to understand phase of matter from the wave function, we better answer all of the questions. So we cannot avoid the figure eight question. But okay. Oh, by the way, maybe I should make a short comment. I claim that you have a simplex theorem without proving, but at least I want to prove one thing. I think I haven't shown you that the information complex set on the figure eight is non-empty. So why is it non-empty? So there is a state. Is no. This follows from the merging theorem. So we can merge two disks to obtain the figure eight. How do we do that? You can partition this into pieces. Maybe let me draw a better one. Let's call this B and C. Intuition is to chop this into halves. A and C, okay, B. Right. B and D and C. So this is C, this is B. So you can convince yourself that ABC is embedded. Is it? Yeah, it's embedded. Embedded in the background, and BCD is embedded. Now, both of them are disks. So you have a reference state on them, and you can check that all the conditions for merging are satisfied, so you can merge them. And according to the merging theorem, the merge state must be in the information complex set. So you constructed an element in the figure eight. But that element is actually is not an extreme point. It's the one with the maximal entropy. You constructed an element that is in the center. Yeah. So this is a real star.
I still have one question. This immersion, why do you not consider manifolds which has the shape of a figure eight rather than to embed it in to reuse quantum states? That doesn't seem very physical.
Why not?
If I have a material
Yeah.
that is made into the shape of a figure eight,
Yeah.
that seems more natural than saying that I'm embedding a disk there and then certain quantum physical spins are reused onto layers of the original manifold. Why do you not consider directly creating a material into the shape of a figure eight?
Yeah, we can consider that. There's no contradiction, but I'm saying even if we don't have the double layer system, we can theoretically construct such state and then put the purpose of a constructed state is to put constraint on the original system.
Okay, you think they're basically the same.
Well, I'm thinking in this way we theoretically do more things without requiring more from the lab. So in the lab we have a single layer material. That's already enough for us to think about these things and understand better about the single layers.
Okay.
Okay. So where am I going? I said there is a puzzle, but actually I want to talk about bridging. So the next 10 minutes will be about bridging. So the take home message is that most the figure eight puzzle I tell you, I believe is a completely, should I say that way? At least the S and T matrices and even the mapping class group for like a general punctured manifold, not just torus, but other manifold are solved based on the idea of you have inverse region and deform them in a certain way and so on. And yeah, and the same idea works in higher dimensions as well. Or maybe let me make a comment for the figure eight conjecture. So the figure eight conjecture here is actually implies some uh, some another conjecture that looks more general and works for any dimension. It's called strong isomorphism. Conjecture of strong isomorphism. So it's like previously the isomorphism theorem said that if you can deform one region to another, then the three information convex set are isomorphic. But the stronger one, what is the stronger one? It requires a let. So it's isomorphic to omega theta is omega and omega theta are homeomorphic. Well, of course, these two must be immersed in the background, in a sphere. So you can ask this question in any dimension. So two immersed regions in an n-dimensional sphere. Yeah, we know examples that they are not cannot be deformed to each other, but nonetheless they are homeomorphic. We can ask whether that's already enough to guarantee that information convex sets are isomorphic. Yeah, I'd like to conjecture this one, and it will imply that this abelianist problem of the figure eight. So if isomorphic in appropriate things, then the quantum dimension of each equilibrium point must match each other, and yeah, and in fact I can prove this based on figure eight. So the 2D, so if the figure eight abelian figure eight problem, abelian figure eight itself, then the strong isomorphism is true. So in particular, for abelian anion theory, this is true. So therefore, true reference state abelian. Yeah. So if we have a reference state with all the equilibrium point on the embedded annulus are abelian, then this strong isomorphism is true. But it should, I feel like it should be true more generally. If it's not true, then it might be even more interesting because then you can find the models with this not true. This is a fancy characterization of phase of matter. You will say, oh, this is the phase of matter that violates this strong isomorphism. That sounds interesting. but maybe there's no such thing. That's a conjecture.
Abelian means that there is no abelian extremal point. There is abelian extremal point.
There exists one abelian extreme point.
Okay, you just need one.
Yeah, just need one.
I see. It means if there exists one, then in fact the whole information syntax of omega and omega tilde are just equivalent. Or homeomorphic.
Yeah.
Okay. Then it would mean that the quantum dimension of everything else, all the extremal points, there would be a one-to-one correspondence.
Exactly.
Then you need to show the existence of one abelian point.
Right. I need one abelian point. Yeah. So maybe let me sketch the proof. In 2D, a general immersed region, any region immersed in a disk, it can be classified by this. So you have a large disk. Mathematicians call it a zero handle. Then you add one handle on that. You have a number of isolated one handle. The number is m. And then you have a number of one handles paired up in the following way. So this is the first pair, the second pair, and so on. You have n such pairs. And with some twist, so you can add some twist instead of having this. You may have the other one add a twist, or the twist is by that. Yeah. So that's the most general immersed regions. So it's omega with m and n. Yeah, immersed in a with possible twists. Immersed in a disk or a sphere. But then the trick is that we can tunnel a figure 8, which give you isomorphism if you have an abelian state. You figure 8 abelian. It's like this. You pick a handle and you try to do the following. You put a figure 8 here and try to tunnel it through. What do I mean by tunneling? By tunneling, to understand this, we first do something more trivial. We do the tunneling of an ordinary annulus. This is a sequence of quantum channel, by the way. Quantum channel.
Oh, sorry. What are the two lines?
The two lines is some handle. So this is one of them. So pick one and do this. Yeah. So this is part of a topologically non-trivial region. Yeah, this is for tunneling an embedded annulus. It didn't do many interesting things, but it actually does something. So if you have charge A, then you merge. Yeah, this is a merging deformation, deform and partial trace. Then you get this one. It actually fills the topological charge onto this one. Let's suppose you have.
Oh, okay.
Yes, suppose you have B. Yeah, some topological charge B, but after that, this is the A fused into B, and then after that you get A fused into B. Yeah, but the topology is straightforward. But how about tunneling a figure 8? Tunneling a figure 8, we find that Oh. Right. Okay. Yeah, like that. Yeah, and yeah, let me omit it, but let's try to imagine it afterward. But the end result would be yeah, adding these tweaks. Right. So the idea is like figure 8 is a generator of a tweet. In two dimension, whenever you have a two homeomorphic region, immersed regions that are cannot be deformed to each other, that must mean somewhere on the region you have a natural twist, and you use the figure 8 tunneling of figure 8 to fix all the twists, then you get what you want. And luckily, if we have abelian sector, any abelian state, the tunneling gives an isomorphism. Otherwise, it will collapse the convex set to a subset. So it won't work.
Sorry. When you say collapse of the convex simplex, what does that mean? Can you say a few words more?
By collapse, I mean it maps an extreme point to a non-extreme point.
Oh, okay. So you mean you start off in this deformation with an extreme point, then you move them, and then afterwards, but how do you see that it's no longer an extreme point when you have that?
Okay. Let me see. Okay, here is one example. So we know that this happens when we have A and B on the tuple, and then we fuse them to this one, A and B. But then if we look at this entanglement boundary, it fused into B, but it's usually a sum of difference B. If you have multiple choices of a fusion outcome, you get a mixture. Yeah, you get a mixture of the choices that give you a non-extreme point.
Oh, okay.
Yeah, it's like this part is a problem.
Okay. But which of the boundaries you are looking at there that might potentially be a mixture?
Yeah, it's a boundary that goes somewhere. So if we, this is a handle connect to somewhere. So this handle, for example, then if you look carefully, I think you will have something goes all the way and back. Yeah, right. Or maybe not, or maybe just here, and then yeah, so, some closed loop. Yeah, but that one may carry some charge.
I see.
Yeah, I think I spent too much time on the strong isomorphism. I didn't even get to the torus. Yeah, but would you mind maybe like 5 more minutes?
Yes, of course, sure.
Right. Okay. So for the two puncture torus, yeah. So this is a torus minus a ball, and we can compete. Yes, to try to purify the region and insert everything to a purification point. Then we get a puncture torus. Torus. The important thing is that the axioms are code everywhere. Including on the completion point. The completion point denoted by a diamond. Yeah. Yeah, every axiom code everywhere. Here, there. And we can prove theorem as information convex set of the torus based on the reference state. This reference state on the torus we construct. Based on this reference state on torus is a Hilbert space is spanned by the annual state. Now, A. And in particular, that checks the intuition that on the topological quantum field theory, the state on the torus give the same number of annuals. So the Hilbert space dimension, and the vector space on the torus will be the number of annuals. Yeah. But then where is the promised S transformation? T transformation will be related to the figure 8, but since we ran out of time, I just tell you the definition of S matrix. The S matrix. Yeah, for everyone learns about mapping class group, I think the S matrix is the mapping on the torus that swaps the two non-contractible loops like this. But on a closed torus, if we want to deform the quantum state, it's hard to imagine how we can flip the two loops by any continuous deformation. But luckily, we have the following procedure. So the state on this constructed, this torus that's constructed from the immersion, we can first remove the ball and then talk about immersed region with the two handles, and the two handles will be colored differently, right? So because they correspond to the two non-contractible loops. Yeah, the two non-contractible loops. But can we? Yeah, the right question to ask is whether we can come up with a deformation on the sphere that swaps the two loops. Now the red one would be this one, and the yellow one will be this one. It turned out the answer is yes. The answer is yes, and yeah, so it's like we have a torus. We remove a ball. Remove a ball, and then we do this and deform this, and then complete, add a ball. Then we get another state on the torus. And the claim is that it's effectively giving enough information to determine that matrix.
So you mean a sequence of moves on a S2 to convert the first geometry to the second?
Yeah. Yeah, and we do need S2. So for instance, we can first try to rotate the region, right? So we have this one, we rotate by maybe 90 degrees or something. Then the red one would be, let me think. Let's start from here, right? This is the red one. The yellow one and after rotation, we get, so the red one will take the place of the yellow one. But then the yellow one will be, yeah, pointing down. So it's somewhere near here. But we want to flip this up. So from down to up, that step needs the sphere. Yeah, then this is on the disk. This is on the sphere. And from down to up. Right. Right. I think I kind of run out of time. But
Next lecture, since it's tomorrow morning anyway.
yeah, okay. Yeah, let me just say that from here we can define the S matrix is unitary. The S matrix is unitary, SAB. We did this in a way that's free from any talking about the string operator. But in a early work of mine, which it was the first time I found the punctured torus, inverse punctured torus was useful. I give another definition of the S matrix using either a string operator expectation value of four string operators or a pair of string operator acting on information convection. In fact, this definition is equivalent to this one. I don't have time to show that. But I also want to say that from the string operator argument, we can also show that the S matrix satisfies the so-called Bernoulli formula in the ABC in sum of X. One X. Yeah, things like that. So Bernoulli.
Don't quite understand how get S matrix components as a number through this process.
Yeah. Good. Yeah, let me talk about the code case. So the information convex set of the punctured torus for the code will be a four-dimensional space, four-dimensional coherent Hilbert space. Or more precisely, the set of states. Yeah. This is the set of state, and you have an automorphism, kind of rotating the block sphere in some way. But that's not enough to give you the label. But the nice thing about this, which I omitted, was that this is not only a block sphere, but also a block sphere with a marked point. How to mark the point? You can ask by what's the reduced density matrix on this annulus from any state here. Usually you end up with a non-extreme point on the annulus, but for special point, special number of points, I think all of them in this example. In the example of Torah code, you have four points correspond to the extreme point labeled by 1E, M, and F when you reduce this to the annulus that's colored red. Yeah, you have some marked point. After you do everything, you get a rotation, but you still know about those special points. Then you take A and B. Yeah, you know about the A and B. Remember, I was thinking that you have marked point on this four-dimensional Hilbert space. And after you rotate, you also know about the marked point. Then you somehow know about the group the matrix element. Right. So that's not an easy task. I'm not saying it's practical. No one have done this in practice. Yeah. But the idea is that after this argument, we know that in principle we can extract the numbers from a piece of local decimation on the ball without knowing the global topology. And I know you have worked by matching class group with a torus or something like that. Yeah. Yeah, thank you so much for today. Thank you, everyone.